All right, let's take a look at a couple simple mathematical tools that help us to make better decisions under two different circumstances. So first, we're going to use the idea of expected value to think about how to evaluate a situation where there are different possible outcomes with different probabilities. So you think about something like playing a hand of poker. Do you bet? Do you fold? Do you check? All of those decisions you have to make before you know what's going to happen. All you know is that you might win, you might lose, and you can calculate some probabilities of different outcomes. The other tool we'll look at is present value, which lets us move through time. It lets us compare, say, getting $1 now versus getting 95 cents in the future. Which one's worth more? Well, in that case, $1 now. Sorry, I get the numbers backwards. 95 cents now versus $1 in the future. Those are harder to compare, right? $1 now versus $2 now, we know which one's bigger. $1 now versus $1 in the future, we know that the dollar now is preferred. But at what point do we start to break even? Right? $1 now versus $1.05 in 1 year means that you're getting an interest rate of 5%. And so if that's a reasonable number, then we've got something close to equivalence. But we'll look at that with the math, and we're going to have a spreadsheet, Google Sheets, do the hard work for us. But let's start with expected value. So we'll start with the simplest possible example, something where two things can happen. So let's say you flip a coin and you get heads or tails. We know the probability of each is 50%. So in this case, I can just say 1 minus our probability here, and this will let us tweak the example a little bit. And then, oops, and I got to update this, but we'll do that in a sec. So let's say we're betting on this. So if you get heads, you get $10, and if you get tails, you lose $10. All right, so the math in this case should be pretty easy. What's the expected value? Well, on average, if you did this bet many, many times, sometimes you'll win, sometimes you'll lose, but on average, you'll win half the time and you'll lose half the time. Let's move this a little bit out of the way. So this, we can just say the probability times the outcome, and then do the same for our other possibility. And then our expected value is just the sum of those different possible outcomes. We just add those together. Sorry, let me move me so that you can see what's going on there. So adding those two outcomes together, and those two outcomes are half of the average, right? When we add them together, we have an average outcome. Now in this case, the average of 10 and minus 10 is 0. But what if we had an unfair coin? What if it's slightly less likely to come up heads? Let's say it's 45% likely to come up heads, 55% likely to come up tails. In this case, your expected outcome is that you lose $1. So if you are playing a game with someone, this heads or tails game, and in the long run you play many, many rounds and you lose an average of $1 a round, you can say it feels like maybe this is an unfair coin. Maybe there's a less than 50% chance of heads. All right, let's do a few other examples. So let's say roulette. You can get red, black, or green. And let's just check really quickly. Roulette wheel. I always forget how many numbers there are on each. Last Wikipedia. French roulette has 1 green. American roulette has 2 greens. Here we go, a double zero wheel. Ooh, I guess someone has a triple zero wheel. Numbers up to 36. So, how many outcomes have we got? What are our probabilities? So we've got 36 plus the 0 and the double zero, which is over here. So we've got 38 total. What is 36 divided by 2? So we've got 18 red spots, 18 black spots, 2 green spots. So 18 over 38. 18 over 38, and then 1 minus those other two. Add those together, and just to make sure our math is fine, adds up to 1, right? Adds up to 100%. All right, so what are the rules of our bet? Let's say we bet 10 bucks on red. If the ball lands on a red square, we're going to double our money. If it comes up to either of the other ones, then we get nothing. Our expected value in this case is $9.47. We put in 10, we expect to get $9.50 back. What that means is that in the long run, we are losing money when we play roulette. Unless you are the casino, in which case, really what's going on here is that you've got minus 20. This is your expected cost of someone else's $10 bet. So I go to your casino, I put $10 on red, you expect on average to have to pay me back $9.50. What that means is you get 10, you give up $9.50, you're 50 cents ahead. This is the basic business model of a casino. So, expected value. What we're doing is we are averaging our possible outcomes, but we're weighting that average by the probabilities, right? So it's not just we add up some numbers and then we divide by the number of numbers that we've got. We take these numbers, we multiply by the probability that they happen, and then we add up those probability adjusted numbers. So in a case where it's win and lose, it's pretty straightforward. Let's do one more. So let's say you are a bank and you issue a loan. So maybe you get paid back. Maybe you get a partial payment, and maybe you get a total default. So you've got this loan. Let's say you loan someone $1,000, and if they pay you back with interest, they're going to give you back $1,100. If they maybe aren't able to completely pay this loan, but they pay part of it before they stop, maybe you get $500, and then if they default entirely, you lose everything. So in this case, with a $1,000 loan, based on these probabilities that we just left over from a roulette game, you're losing money on average, right? If you're a bank making loans like this, you're giving away $1,000 and getting back $750, you're going to be out of business after a while. All right, so we need to think, what are the actual probabilities that someone pays back their loan? This is going to depend on how their credit looks. So maybe there's an 80% chance that they pay you back, and then maybe there's a 15% chance that they pay back half of the money without interest, and then the remaining 5% chance that they don't pay you anything. And again, we're losing money in this case. So if you are a bank, you're going to have to, if you're a bank and you have good reason to believe that the probabilities of these outcomes look like this, you might have to charge more interest, right? So now you give out $1,000, you get back $1,035. Here you're effectively getting 3.5% interest. Anyone who pays you back is paying 20% interest, but on average you're getting 3.5% interest. So this is like a credit card, right? So if 80% of people pay off their credit cards, 15% of people make some of the payments and then disappear, and then 5% pay nothing at all. If you are a credit card company looking at these sorts of outcomes, your expected value really doesn't look that great. Right now, as I'm recording this, you can get a 4% government bond. So you're going to have to adjust your business model if you're in this case. But more important for our purposes, this is a nice simple application of the concept of expected value. And what this lets us do is take three potential outcomes and smush it into a single number that we can think about before we find out what actually happens. So we give someone $1,000, we hope they pay, but we don't know that they're going to pay. After the fact, we find out if we get paid or not, but we can think about, is this a good idea to do this before we're in too deep, by thinking about what are our outcomes and what are the probabilities that we get to those different outcomes. All right, now let's look at present value. So this lets us compare different opportunities where one is in the future and one is in the present. right? Or 2 are in the future or whatever. But it lets us treat future payoffs in a way where we can compare it to present costs or present payoffs. So our relevant concept here, or sort of a key concept behind the scenes, is the idea of a discount rate, or you can think of this as an interest rate. So if you think about something like, I'm going to sign a contract where I agree to pay you $100,000 in the future, you have to think, well, how much should such a contract be worth today? And to figure that out, you have to think about what would happen if you, instead of doing this, you just put your money in the bank and got some, interest on a certificate of deposit or something like that. Or you could think about, again, using the term discount rate, we can think about, if I promise to, say, pay you $1,000 in a year, you know that $1,000 isn't going to be worth as much as it is today, for example, because of inflation. So if you expect the money's going to be worth 5% less in a year, then my promise to pay you $1,000, it's really more like a promise to pay you $950. All right, so in a case like that, how much is this contract worth? Well, it's closer to $950 than it is to $1,000. All right, let's take a look at the math really quick. So, present value. Did it wrong. Wikipedia, present value. Or actually, you know what? Investopedia will do the trick. We'll open Wikipedia also. So Investopedia is pretty good for this sort of thing, except they got all these ads. Criticism, future versus present value. Here we go. Here's the formula. So this is just sort of the flip side of the formula for future value. So when we think about something like, you put at time 0, you put, say, $100 into a bank, we know that with 5% interest after 1 year, let's call this future value, the future value of $100 after 0 years is the same as the present value. But after 1 year, it's going to be this times 1.05 is 105. After 2 years, it's going to be this times 1.05, $110.25. That's how we're going to grow our money. And the formula for that future value is the present value, so the $100 that we put in initially, and then our formula for interest, we usually say 1 plus R, or 100 plus the discount rate, divided by 100 to give us 1.05, to the power of the amount of time that passes, right? So after 1 year passes, this is the equivalent of 1.05 to the power of 1 times 100, right? So what's 1.05 times 100? It's 105. If we say 1.05 to the power of 2, we're getting 1.1025. So 100 times that gives us 110. Now notice here, we didn't use the exponent because we were multiplying by something that had already grown by 5%. So in a spreadsheet, it's kind of easier. We can skip that 8th grade math of exponents. And, even though, we've all passed 8th grade, we know how to do exponents, it's still an extra moving part. So this might make it a little bit easier to avoid making a silly mistake. But let's go ahead and do it the right way, which is we do a little bit of algebra and we move our formula into this form where we have present value on the left-hand side. So future value divided by future value equals present value divided by future value times 1.05 to the power of t. And then this is just 1 equals present value over future value times 1.05 to the power of t. And then let's get the present value out of there. Now, let's skip some steps. You guys don't want to watch me do algebra. Basically, we do the algebra, and what we're going to get is present value equals future value divided by 1.05 to the power of t. Right? Or a little trick that might make this a little bit easier in Excel, multiply by 1.05 to the power of negative t. does exactly the same thing. Right. So the math is not terrible, but also if it doesn't fit in your head, don't sweat it. I mean, I would encourage you to practice, right? This is, simple math, and being able to feel comfortable with it is going to help you in the future when you have to think about how your mortgage is going to work, or your car loan, or investments, your retirement account, all those things. Definitely do the math, but don't sweat it as far as grades. Don't stress out about it right now. So we've got this formula for present value. Let's clean stuff up a little bit. Our present value equals what we're going to get in the future times 1 plus this. Let's see if Google automatically converts that. Actually, let's see what happens. We'll put 1 in. Oh, cool. It did that. Nice. So in Google, I'm not sure about Excel, not sure about LibreOffice, but in Google, we can just say 1 plus 5%, and it converts it to 1.05, which you can barely see here. Maybe you zoom in. To the power of time. So, can we see this? There we go. That's not what I want. Here's our formula. Whatever is in cell B4 times 1 plus B1, that's our interest rate up here, to the power of A4, that's the amount of time, right? So we start at 0. So let's imagine I promise to pay you $1 a year, right? Or if you want to make it more fun, let's say $1 million a year. And let's say I plan to do that for 25 years, or I guess 26 years, including right now. So you get $1 now, and then $1 for the next 25 years. So our total future value, if we just add it all up, is going to be 26. Equals this, equals the sum of all this. Right? So we're getting $26 million over 25 years. Is this worth $26 million? Well, no, because some of this money we're getting a long time into the future. So from my perspective, if I win a lottery that says we're going to pay you $1 million a year for 25 years, the $1 million I'm getting in 25 years is not worth nearly as much as the first million, right? So I have to discount that number to make it a figure that I can compare, right? To think about how much is it really worth now. A simple intuitive way to think about that is how much money would I have to put in the bank to get $1 million after 25 years, right? If I put money in the bank now and I let it sit, what's the present value such that the future value I end up with is $1 million, right? That's what this second equation is telling us. So let's take this, and I'm going to add a little bit. I'm going to add a dollar sign here, and a dollar sign here. Whoops, actually, don't want the dollar sign here. I just want the dollar sign for the interest rate. Let me show you the formula there. That dollar B, $1, this means that when we copy this formula down, the B4 and the A4 are going to become B5 and A5, but the B1 stays B1. Right? So what we're calculating in this cell is this number times 1 plus this number to the power of this number. Right? So this number times that stuff to the power of this number. And we copy that all the way down. And then while we're here, let's look at the sum of that. And let's look at what we actually calculate. So $1 right now, after 0 amount of time, that we have to wait 0 amount of time to get, is worth $1, right? Or $1 million is worth $1 million. Oh, did I do this backwards? I forgot the negative sign. There we go. $1 million in a year is worth a little bit more than 95% of that at a 5% discount rate. And $1 million in 25 years is only worth $300,000 in present value terms. If you put $295,302.77 in a bank account getting 5% interest per year, after 25 years, it will grow to be $1 million. So we add up all of these numbers, and what we get is that this contract is worth about $15 million, not $26 million. So if you are running the lottery, right, if you get a job working for the New York State Lottery, what you can do is you can advertise this as a $26 million prize, but you only need to actually find $15 million to have this prize, right? Your cost is, you got to get $15 million, so you sell 15 million tickets, you put the money from that into an account, and then it will grow over time to be able to make each of these payments to your winner, right? You need, a little more than 15 million to cover the cost, but you're probably going to sell more tickets so that you actually make a profit, right? And this is how the lottery works. They sell, actually, hey, this is another good example. So if we go New York State Lotto, let's take a look at some examples. And let's see if we can't put the two together. All right, so Mega Millions, you're getting some money, at some point in time. Is there one? Here we go, Cash for Life. So you pay $2. Let's go ahead and create a new sheet using both of these tools. So ticket price is $2. And let's make this all size 18 so you can read it. All right, ticket price is $2. What is our game details? Choose 5 numbers, yada, yada, yada. To win, match the 6 numbers, blah, blah, blah. Find a retailer, choose your playlist. How to claim your prize, multi-draw, yada, yada, yada. We got the odds. We're going to come to this in just a second. Oh, here we go. All right. So we got the prize itself, $1,000 a day for life, and we got some odds. So we've got some outcomes. So Cash for Life. We've got probability, and this is 1 in $21 million. No, I don't think it likes the commas or the spaces. There we go. So your probability of winning Cash for Life, very, very, very small. We'll figure out the value of that in just a second. Let's look at the other prizes. So your second prize, $1,000 a week for life. Per day, $1,000 per week. $2,500. This one's going to be relatively easier. 1 in 79,440. What was this? 1 in 7.3 million. Oops. That was a 3, right? Cool. So we got these probabilities. We can see here this probability is relatively easy to figure out. 4th, 5th, 6th. This is for 500. I'm going to skip a lot of the actual math, but you are absolutely encouraged to do the details. So actually, let me go ahead and skip to that part. So let's think about what $1,000 a day is worth. Payable as a 4-life annuity, minimum of 20 years of $365,000 a year, or a one-time lump sum payment at the election of the winner. Now that lump sum is going to be less than 365,000 times 20. Right? They're going to be using this sort of math. The amount of the lump sum payment is equal to the estimated cash required to purchase the annuity. Right? So exactly the sort of thing we're talking about. Top prize will be divided. Okay, that's going to mess with our actual outcome. So if 2 people win, you actually get $500 a day. But let's not worry too much about that. Let's think about what $500 a day, $1,000 a day is worth. So we're getting $365,000 a year. Let me actually show you very similar to present value. Let's actually mess with this just a little bit. So let's make this equal the sum. Whoops. equals the sum of all of column B and equals the sum of all of column C, except for this 5%. Can I move this over here? And there we go. All right, that did fine. Now let's think about what would happen if we did this for a very long time. So in the near future, $1 million is worth almost $1 million, right? But it's worth less and less each year. It's never going to go to zero, but it's going to go closer and closer to zero, right? So after 150 years, if you put $6,000 into the bank with 5% interest per year, it's going to grow to $1 million in 150 years, right? So if you want to be a millionaire, all you got to do is go back in time 150 years. So if we keep doing this, this is going to get closer and closer and closer to zero, to the point that it barely really even matters, right? So after almost 400 years, we have enough zeros that we're putting pennies in there. What happens is this kind of in the limit goes to zero, right? It's asymptotically going towards zero, and it turns out there's actually a much simpler way to figure out this future value, right? So look at this, it's 20.99999. So the future value is $397 million, right? We're getting 397 payments of $1 million. But the present value is getting closer and closer to $21 million, but it's never actually getting there. So the math for this, and let's assume really quick that you don't get a payment right away, but we just think about what you're going to get after the first year. Your future value is going to be the payment in the first year plus the present value of the rest. And actually, sorry, that should say present value, not future value. So your present value is the payment in the first year plus the present value of the rest of this situation. That second term, this is what is the present value of $1 million a year forever. Now that sounds like it should be infinite dollars because forever is infinite time. But it's actually really simple. It's just a question of how much money do you put in the bank now so that you get $1 million of interest every single year. At 5% interest, if you put $20 million in the bank, let's call that 20, that times 5% gives you $1 million of interest. So after a year, you've got $21 million, then you spend $1 million of it, you're left with 20, and then after another year, you get another $1 million of interest, and every year, you get that $1 million, you take it away, you're left with the $20 million you started with. That $20 million is the value of this second term for the numbers that we're dealing with here. Now, really quickly, while we are here, let's just take a quick look. Let's pull this up where we can see it. Take a quick look at what happens if we mess with the discount rate. So, what happens if we have a lower interest rate? Now, pause and think about it for a sec. Mathematically, it might help you. Intuitively, what's going on is with a lower interest rate or lower discount rate, we're discounting the future less, which means we are thinking it's worth more, which means we are more patient. So, with one, our present value jumps to $99 million when we're getting all of these payments. Let's go back to what we started with 25 years. Take this, delete all that. All right, so that $26 million over time is $23 million in present value terms compared to what it was before of $15 million. If we get less patient, our value goes down, right? So the higher the discount rate, the less patient you are, the less valuable future money is compared to present money. So the higher your discount rate, the lower your present value. But whatever the figure is, it's letting us basically compare apples and oranges. It's letting us compare future money versus present money. All right, let's come back to this example. So $1,000 a year for life. Let's simplify the problem, and let's say $1,000 a year forever. What does that mean? That means we're getting $365,000 of interest every single year. And to get that, we need to put away some amount of money that's going to generate that level of interest. So again, let's say we've got a 5% interest rate. So if we divide our payment, let's simplify really quick, right? So let's say $1 million divided by 5%, we're going to get $20 million, right? $20 million times 5% gives us $1 million of interest that we're getting, and we can get that every single year, right? Back to our 5% interest. $365,000 a year forever at a 5% discount rate is worth $7.3 million. So you put $7.3 million in an account getting 5% interest, you're going to be getting $1,000 worth of interest every single year. All right, so that is the value of this prize, or this is an estimate of the value of this prize. The actual value is going to be lower, right? Because it's cash for your life, not forever. So it's not as much, but just to simplify, this math is easier than trying to figure out what is the value, or, let's, do 25 rows or figure out how long you're going to live or whatever all that is. Or you can look up Investopedia annuity formula. And, oops, okay, no such luck. We'll just ask the internet. So, I knew Investopedia had it, but there's ways to calculate this a little bit more precisely, and with interest we can get a little bit more precise than this sort of relatively simplified version I'm doing, where I'm thinking of just 1 year at a time. We're not doing continuous interest or anything like that. But long story short, what we can do is we can use the concept of present and future value to convert $1,000 a day into $7.3 million now, right? So it sounds like they're offering you a lot of money, and $7.3 million is a lot of money, but it is not $1,000 a day times the number of days that you will live. All right, so I went a little too long on that last example, so if you're still here, thanks. And again, I encourage you to go to the lottery page and play around with these figures just to figure out what is the probability. Now, in this case, we've got two layers of math. We've got the present value math, and then we've got the expected value math. The other prize is the expected value is a little bit easier. So I'd encourage you to start with the simpler ones, right? Figure out what are all these numbers, right? So this is going to be, let me just do one more step for you. 1 divided by 26,000. Oops. Where'd I go? 1 divided by 26,000, that probability times the size of the prize. So this part of this lottery, the expected value is a penny, right? Just about 2 cents. But 2 cents plus 3 cents for this prize plus 33 cents for this prize. If you're paying $2, we add up, all the numbers that we put in here. Well, realistically, if we're seeing numbers around these size, it's called 0.5, whatever. We figure out whatever these numbers are, we add them up, and we can compare it to the ticket price and see how good or bad a deal this is. All right, let's stop there. So our big ideas, expected value and present value. The intuitive versions of these, expected value lets you think about something that it's going to be one thing or another, but you don't know yet. So you need to average those outcomes, but you need a probability weighted average. So expected value lets you think about a scenario where many things might happen, but you can still compress it into a single number that you can compare to something else. With present value, we are able to compare the value of money in the future to money now by thinking about how impatient we are, or what if we just put our own money in the bank and let it grow at whatever our relevant interest rate is. Maybe it's 5%, maybe it's 15%, whatever the case is. We use the discount rate to ask basically how much less should money in the future be considered to be worth compared to money right now. And then we can also put those together to think about a situation where maybe you have a stream of payments in one case, or explicit one-time payments in the present. We put these two together and it makes it easier for us to make comparisons that seem like they're apples to oranges comparisons, right? It lets us make an apples to apples version of this. All right, so as usual, if you have any questions, let me know in the usual places, and I'll talk to you in the future.